It's a pleasure to be here talking to this audience. So I'm going to talk about learning models and constraints with limited data. And here is a quick, here's a quick outline of the talk. So I will try to motivate the role of data in control and autonomy in general. Then the talk will have two parts. The first part, I will talk about sample complexity analysis of a traditional system identification method due to Ho-Kalman. And in the second part, if I have time, I will talk about inverse constraint learning. And this is also related to an idea by Kalman called inverse optimal control. And the first part will be system identification. The second part will be robotics, if we have time for that. Okay, so here is my view of any control problem. So if you have a control problem, you typically have a model, a plant model that you want to control, and you have a task, a specification. It could be stabilization, it could be optimizing a cost function, it could be satisfying some constraints. And given this plant model and what you want to achieve with the plant, you go and design or synthesize a controller. And you close the loop, and you want to ensure that when you close the loop with this controller, your plant satisfies the specification in the closed loop. Or you want to come up with a proof that this is impossible, so that you can either improve your model or you can relax your specifications to something the plant can satisfy. And traditionally, there's not much data in this process, but you can use data in several different ways, and you can incorporate data in this process. And there are roughly two ways to incorporate the data in the process. One of the ways is you use your data to construct your models, or you use your data to construct your specifications. And using data to construct models is system identification or learning your dynamics. And using your data to construct your task specification is more like imitation learning type ideas. And you can use data, construct your models and tasks, and you are back to your original problem. You have a model, you have a task, you want to design a controller. This is usually called model-based learning because we are using models in between. And there's another way of using data to directly go to control. Without constructing this intermediate objects of models and task descriptions. And that's usually called model-free learning. This talk will mostly be about model-based parts, and I will try to motivate and tell you why I like the model-based paradigm better. And in the first part of the talk, I will talk about going from data to models. And models are useful for control design. If you have a model, you can use rich history of control to design your controller. If you have a model, you can do fast simulations of your system and maybe generate predictions of the future from this model. You can use this model for monitoring your system. And you can also use the model for anomaly detection. And in this talk, I will be interested in building models using small data rather than big data. And here are some motivating examples for cases where you might have small data. For example, if you are sending a rover to Mars to explore an unknown environment, it's very hard to collect data a priori about how the surface interface of the rover with the Mars surface will be. So you really don't have the chance to collect lots of data if you are going to an unknown environment. Similarly, if you have a plane and if your engine of this aircraft blows up in air, again, you don't have that much time to collect data. You need to figure out the new dynamics as soon as possible. And you need to safely land this plane if possible. So that's going to be the focus. We will try to, on the fly, learn the model and try to use this model possibly in some other objectives. And this allows us to do adaptation. So if we are learning models, especially in this fault failure handling settings, Once you have the model, you can start like repurposing or changing your objectives, because now you have this new model. You can look into what you can achieve with this new model. And based on that, maybe you will say, okay, with this plane, I was gonna go to Montreal and it's not possible anymore, so I should land. So you can change your objectives because your model has changed. So in the second part of the talk, I will talk about, if I have time, I will talk about going from data to task specifications. And why task specifications are useful. Again, if you have a task specification, depending on the specification, we have techniques in control for designing controllers to satisfy certain constraints or optimize certain cost functions. If this task specification is in terms of constraints, you can also use it for monitoring the system. At runtime, you can check whether your system is satisfying these constraints, and you can do anomaly detection. And again, I will focus on the small data regime where you are trying to learn the task with minimum number of data samples. And the motivating example here is that imagine a small manufacturing setting where you try to incorporate a robot arm, and each time the task changes a little bit, you want to reprogram the robot arm, and maybe a person teaches the robot how to handle the new object, and you don't want your employee to spend days to reprogram this robot, to spend days to demonstrate the task, because then demonstrating the task to the robot takes more time than doing the task yourself. So if we want this like flexible manufacturing systems to be incorporated in small businesses, we ideally want a way to teach these robots these tasks with minimal number of demonstrations. And this is gonna be the sort of motivation for this thing. And the advantage here is that once you learn the tasks and constraints, you can generalize to new environments in the sense that, for example, I change the robot arm that I am using. Since I know the task, I can reprogram this robot arm without running any new experiments, because I am assuming here I know the model of the robot arm, and I learned the task that I am trying to achieve with another arm. Then I will just put this constraint and I will solve a constraint control problem with that. Okay, so this is the motivation. Now I am gonna get into the technical part, but I can stop and ask if there are any questions on the motivation so far. Okay, is there a question, or if not, I will just continue, and feel free to interrupt me anytime. I will be happy to take questions on the fly as well. Okay, this first part, I will talk about the system identification algorithm, and this is joint work with my colleague Samet Oymak from UC Riverside. Okay. So we are interested in identifying linear time invariant systems in state space form from one trajectory of inputs and outputs. So we are given some input and outputs, and we want to learn these A, B, C, D matrices. And we are assuming this input and output is generated by a system of this form with some noise, both in the process and in the measurement equations. And this is a well-studied problem in system identification for a long time. And there are two different types of analysis you can do here. One is the asymptotic analysis. Can you come up with a system identification technique that in the limit as number of data points n goes to infinity, or the noise level goes to 0, can learn the system model or some invariant of the system model. And the other perspective is non-asymptotic analysis. Given finite amount of noisy data, if you're applying a system identification algorithm, how does the accuracy of your learned model depend on data size and noise level? And another question you can ask in the non-asymptotic regime is that what can the best identification algorithm achieve in this non-asymptotic setting? And in this talk, I will be mostly dealing with the non-asymptotic case. These are both problems that are studied in different fields. Asymptotic analysis is something statisticians do a lot, so they study consistency of all estimators. And this is also studied a lot in the history of control. So if you take the textbook of Leonard Leung on system identification, he presents different model structures, different estimators for different model structures, and analyzes asymptotically how these estimation and learning or identification algorithms work. And there are lots of standard methods for linear systems, in particular in state space form. One of these methods is due to Ho-Kalman. The original method is algebraic without any noise. I will go over the methods really quickly. But in practice, it's also used a lot with noisy data. And that noisy data version is typically called eigenrealization algorithm. So that's going to be the algorithm we will analyze. But there are other like subspace identification techniques. One popular one is and for society. So on the non-asymptotic setting, this is also studied in control. So there are like papers by Vidyasagar and Weyer and Campi that studies kind of sample complexity of system identification. And this is a relatively recent review article that covers some of the techniques out there for non-asymptotic system identification for control. But one of the limitations in these techniques is that most of these techniques have something called a noise invertibility assumption, which essentially means that if you know your system model, can you uniquely invert the noise? And if that assumption holds, then you can apply these techniques. But in our setting, that noise invertibility assumption does not hold for the model structure that I showed you. So there are also like lots of non-asymptotic analysis techniques coming from statistical machine learning community more recently. People have been looking into non-asymptotic analysis of simple least squares type problems. And then they started looking into more dynamic problems where you have this time dependence between your samples. And here are a few papers along those directions. Of course, I am missing the very recent sort of works in this domain. It's kind of, there are lots of things out there right now, and I will try to get back to that in the end a little bit. But one of the missing parts of this earlier techniques is that they didn't go and analyze existing system identification techniques. They simplified the setting. They said, okay, I am gonna do system identification, but I will assume I observe the state. And it's not very common in system identification to assume you observe the state. Then your problem looks a bit more like regression, because you are observing the state, you are trying to learn your A and D matrices. And in those settings, they brought very interesting tools from statistical machine learning to do system identification. So this is going to be the thing that, or this was the thing that motivated us. But we said, okay, why not go to this simplistic setting? There are lots of traditional system identification techniques. Can we just apply these type of ideas in analyzing more traditional system identification techniques? And this is going to be what I am going to talk about. So we will focus on this Ho-Kalman algorithm or eigenrealization algorithm, its noisy version. And we will provide a sample complexity analysis on this algorithm. And one thing we realized in doing so is that there wasn't really a good understanding of noise sensitivity of or robustness of Ho-Kalman. So people use this with noisy data all the time. But it wasn't clear if you have some amount of noise in your data in applying Ho-Kalman, how does that noise or error propagate through this algorithm? And we will do that analysis as well. Okay, so this is the plan. So this is just a very quick overview of the Ho-Kalman algorithm. As I said, it's very algebraic. There is no noise whatsoever. So you have this data as time goes from 0 to n and inputs and outputs. And you have a model of this form, you want to learn ABCD. Of course, this identification problem is ill-posed. We can only learn up to a similarity transformation. So this is like basic linear system theory. You can never learn ABCD because for any invertible P, this alternative system will give you the exact same input-output behavior. So we can therefore only learn up to a similarity transformation. The other thing is that you can never learn ABCD if your model is uncontrollable or unobservable. And you can only learn the controllable observable part. So we will just assume the system is controllable and observable. And Ho-Kalman proceeds in 2 steps. In the first step, you estimate Markov parameters of your system. So these are the Markov parameters. And if this is a single input, single output system, Markov parameters are essentially your impulse response. And the nice thing about learning Markov parameters is that Markov parameters are invariant to the choice of basis. Now we are learning an invariant. We are thinking about something really learnable or identifiable. And in the second part, you take these Markov parameters and you try to estimate system matrices from this Markov parameters. And I put the system matrices in quotation here because, as I said, you won't be able to learn the true ABCD, but we will learn one canonical form out of them. Okay. So now I will first describe you how to estimate system matrices from Markov parameters. I will start with the second step. Then I will go back to the first step and show you how to estimate Markov parameters from data. So this is what Ho and Kalman did. So assume you are given the Markov parameters of the system and assume these are correct. So there's no noise whatsoever. You have these Markov parameters. From them, you form a Hankel matrix. Hankel matrices are matrices where anti-diagonals are constant. And if you look carefully in this Hankel matrix, one thing you will notice is that this is the multiplication of an extended observability matrix and extended controllability matrix. So it always has rank n, assuming you pick your number of columns or block columns and number of block rows in a way that the dimension of this matrix is larger than your system order. So what Ho and Kalman did is that they discard the last column of this Hankel matrix and they called this is another Hankel matrix that's essentially formed with neglecting the last Markov parameter. They called this guy H plus, and they discarded the first column or block column if you have a multi-input, multi-output setting, and they called this one H minus. And H plus is still a multiplication of an observability and controllability matrix. H minus is similarly multiplication of an observability matrix and a controllability matrix, but there's an A matrix in between. Then given that, what you can do is you can take your H plus, you can do an SVD there. We know this is rank n, so this is gonna be an exact SVD. Then you can set your observability matrix as U times sigma square root. You can set your controllability matrix for this remaining factor in your SVD. Then you can pick your C bar, the estimated state, as the first m rows of O, because your observability matrix starts with C. Similarly, you can pick your B bar as the first P columns of Q. Then using this relation between O, Q, and A, you can solve for A bar as well using your H minus. And typically, if this was an infinite Hankel matrix, the sigma is something we know from control theory. The sigma contains Hankel singular values of our system. And this ABCD that you construct is a balanced realization that sort of orders your states in the sense of their controllability and observability. Okay, so what happens if you don't have the actual Markov parameters, but you have some estimates of these Markov parameters? Now, instead of the true Markov parameters, you are making some error. And this is eigen realization algorithm. You just like go ahead as if there's no error whatsoever. You form your Hankel matrix. You do the same thing. The only difference is that your SVD is no more exact, because since you have errors in the entries of this Hankel matrix, this is no more gonna be exactly rank n, but you just do a rank n truncation using SVD, and you proceed as usual. Now the question is, this is used a lot, but how much do we lose by doing this? Is the ABCD that I am finding any close to the original ABCD? And I am not finding D here because D, I already have an estimate of the D. If I have this noisy estimates of my Markov parameters, the first parameter here will be my D. Okay, so this is what we have analyzed first. So given a bound on how much error you have in your Markov parameters, and given that this is the algorithm that you use, how good are your estimated ABCD? So the first thing you can do is to figure out, given these errors in G's, how much error you are making in H. And a crude bound for this is essentially just counting the number of times that these entries repeat in your H matrix, and you get something that looks like this. And from this, using the properties of singular value decomposition, you can also figure out how much your L had, the low rank estimate of H deviates from L. And if you further assume this deviation of L hat from L is small, then we show that there exist unitary matrices, P, such that the C bar, B bar, A bar is close to the true balanced realization. And this is the degree of closeness. So there are a few things that are interesting maybe to point out here. This sigma min of L is your minimum non-zero singular value, Hankel singular value. And it essentially tells you how observable or controllable your least observable controllable mode is. And if this thing goes to 0, then it's going to be harder to estimate your system. And essentially, you are seeing this over here. As your system becomes less controllable and less observable, it hurts your estimates. And the reason why we have this condition or assumption here is essentially if your least controllable and observable mode is such uncontrollable and unobservable so that the noises, the amount of noise you have sort of overrides this mode, then you cannot learn. So essentially, to be able to learn all the modes of your system, you need each mode to be sufficiently controllable and observable. And essentially, this assumption is capturing that thing. Okay, any questions so far?
Maybe I have a clarifying question. So the norm for this L, these are what type of norms?
These are all spectral norms. If I put F, it's Frobenius norm. The others are just matrix 2 norm.
Thank you.
Okay. So this was kind of surprising in the sense that people have used this eigenrealization algorithm all the time, but there wasn't any analysis in terms of like how much error you make. To tie the two pieces we had to do this analysis. This can be improved a little bit, and I think there's at least one paper from KTH that improves these bounds a little bit that came up probably this year in 2022. Okay, so what we have shown so far is that if I have some estimate of the Markov parameters, I can use my Ho-Kalman algorithm and get estimates of my states. The question is, how do I estimate these Markov parameters? And here we will make some assumptions on the noise and the input that we are using for identification. We will assume the noise terms are Gaussians, and the input itself is a Gaussian as well. And for simplicity, we will assume our initial condition is 0. This can be relaxed easily. So if this is the setting, cross correlation of inputs and outputs essentially give us the Markov parameters. If I can compute the expected value of yt ut star over sigma u square, then this is essentially gonna give me my Markov parameters. And if I look at this y and u with time difference of k, that's gonna give me the kth Markov parameter. So if I can somehow compute these expectations, then that would give me a way to compute my Markov parameters. And if I had independent yt-ut pairs, then estimating expectations are easy. So we can just do sample average, and that will give us estimations of these expectations. But since I am interested in learning these things from a single trajectory, I cannot just go and do sample averaging. If I had multiple independent trajectories, then I could simply estimate this expectation using averaging. But since I have single trajectory and I don't have independent yt-ut minus k pairs, averaging won't help. So what we will do instead is we will try to write a least squares, ordinary least squares type problem. So to do that, what I am gonna do is I will try to write, I will split my data into windows. And assuming I am just trying to estimate t Markov parameters, I will try to write yt as a function of the u's in this window of size t and the initial condition at the beginning of that window. And I can do this for each of these overlapping windows. So yt plus 1, I can write it as a function of all the u's in this t-sized window and x1 and so on. So these are just different windows of size t. From that, I can try to learn my first t Markov parameters. So again, you can do some simple algebra. And for all these y's, I can write them as a function of all the u's, the noises, and the initial condition of that specific window. And if I sort of rearrange these terms, one thing I will observe is that the coefficients, matrix coefficients here multiplying u's are essentially my Markov parameters. The coefficients that multiply this noise term W is an observability matrix from noise to output, that's F. This Z is over here, and there's some effect of the initial condition, and I will just lump it into a term, ET. And I will treat all of these as noise, and I will do something simple. It's not the best estimator, but it's an estimator. I will just do a ordinary least squares to solve for G by treating everything over here as noise. So this is how I am gonna write my estimation problem. So I want to find an X such that I can write my YT as X times U bar. And I want to minimize this for all the windows that I have. And this is going to be my G hat. So in a sense, this is kind of fitting a FIR model to my system because I am trying to estimate Y as a function of past U's. The nice thing about this estimate is that we can solve it in closed form because this is ordinary least squares, and that makes analysis easy. So then the question is this a good estimator for my Markov parameters? And that's what we are going to analyze next. But let me stop here and see if there are any questions.
So I have two, two clarification questions. One is, so just so that I understand correctly, right now, you're effectively treating ET as noise as well by just ignoring that in the least squares.
Yes.
Okay. And in a previous slide, you had written this expression for cross correlation, expectation of, yeah, this one. So just what is U star here?
It's just, since these are in general matrices, it's the transpose, conjugate transpose in general. These are real. So in the multi-input, multi-output, since I am doing multi-input, multi-output setting, this is going to be YTU T minus K transpose. You can imagine. Okay. That way.
So you're imagining everything is in complex, just.
Yeah.
With, okay. All right. Okay. Yeah. Thanks.
Okay. So this is our ordinary least squares. We know how to solve it. It is a nice closed form expression. And to write the nice closed form expression, what I will do is I will concatenate all the data in this n bar windows that I have, so that I will be able to write my Y as a function of the true G and U. This is the concatenation of W. So these are circulant matrices or Hankel matrices of U's, Hankel matrices of W's. This is Z and E. And if I write this way, note that I am ignoring this part and I am fitting this thing and trying to find my G hat. So I can write the expression for my G hat using simple pseudo inverses. So this is going to be my G hat in matrix form. And here what I am doing is I am just taking the true expression of Y and plugging it in this expression for G hats. And if I do that, I can write G hat in terms of the true G and some other terms. And from there, I can also write the difference between G hat and G. And I will do a simple triangular inequality matrix submultiplicative property type things. And if I want to bound the spectral norm of G hat minus G, I need to bound all these terms on the right. And if I can bound on all these terms with high probability, that's going to give me a high probability bound on G hat and G. So for all of these terms, the green ones, we can use some concentration inequalities for matrices. The only trick here is that the entries of these matrices are not IID because there are repeated entries because these are Hankel matrices. And it turns out that there are some concentration inequalities for circulant matrices. And Hankel matrix can be embedded into a circulant matrix. So you can use those concentration inequalities to bound these terms. This one is a little trickier because this E is not independent of U. In these ones, I have all independent terms. It's just that my terms are repeated. But here I have true dependence between terms. So I need to use some martingale type arguments to bound that. But if you do those, you can come up with this theorem that says if your data size is larger than this thing, then with very high probability, this error over here will look like this. And if you look at these terms, essentially, this entire thing is a signal to noise ratio type term. If my input is large, I am learning better. If my noise is large, I am learning worse. This F is the observability metrics from noise, process noise to my output. So if this noise is more observable in the output, it hurts me. And in terms of number of samples, I am scaling with 1 over square root of it. So this is essentially the type of bound that we can get. And you can rearrange this and say things like, oh, given some delta and epsilon, can we find an n bar such that if I have an input-output sequence of length n bar, with probability 1 minus delta, I will be able to estimate my system matrices up to an accuracy at most epsilon. Or you can ask the opposite question. If n bar is given and delta is given, what's the epsilon that you are achieving with high probability? So this has several extensions and applications. Since we are using Hankel matrices, we can also give you estimates of the error of the learned system in terms of H infinity norm. You can also estimate system orders. Again, this comes from Hankel metrics. If your noise is, again, lower than your minimum singular value, you can estimate the system order as well. And people looked into other extensions as well. So here's a quick numerical example. So one of the ideas that were used earlier in analysis is that, oh, I forgot to mention something. Here we are assuming the system is, your A matrix is stable, and that comes into play in analysis. So that essentially makes this E term, that's the effect of the initial condition, that E term is not large. And the reason that E term is not exploding is that we are assuming the system is stable. Let me go back maybe to clarify. Here, if A matrix is stable, this A to the T term is asymptotically shrinking. That's why this ET is small, and it gets smaller as T grows. So based on that idea, people in slightly different settings, to make the analysis easier, they use this idea of using windows, but using windows separated far away. And due to this asymptotic decay, if you use this separation, you can more or less treat the data in these different windows as independent. And that simplifies the analysis, but you're of course discarding data in that case. So we use that as a comparison. And as you can see, if you don't do any separation, you estimate much faster. And if you start doing the separation trick, your estimates get worse. So we are using practically very good use. We are making practically very good use of data, and we still can get this tight statistical bounds. Here are some more recent results that's of course an incomplete list. So there are two maybe performance criteria here you can look at. One is how many samples do you need so that your analysis is valid? So the minimum time that your analysis starts being valid. And the other one is the rate of accuracy as a function of the number of samples. So, and the other things you can look at is what type of systems you can handle. So we can handle multi-input, multi-output stable systems. We work with single trajectory. This is the rate we achieve. And our rate starts working when we have number of outputs time t samples. And this is essentially the number where your least squares problem becomes overdetermined. So if you are below this, your least squares is underdetermined. So this is, if I am estimating t Markov parameters, this maybe makes sense, but the internal complexity of the system is really the state dimension. And there is some extension where you can drop the dependence, or you can start making these things work with just p times n samples. And to do that in this work, Meryem Fazel and Yu Sun and Samet Oymak, they did a OLS with nuclear norm regularization on the Hankel matrix. And if you do that, you can drop this to the actual dependence on system complexity, which is n. Then there are extensions for unstable systems. If you do multiple trajectories, you can start handling unstable systems. And there's also work by Salar Fattahi, a colleague here at Michigan, that drops the number of samples to a logarithmic term in TP. And this is again using stability. If you have a very large order system, essentially you can get a very good estimate of this large order system just by taking a log t Markov parameter. So that's kind of the idea there. Again, this is not least squares, using a bit more involved optimization techniques for sort of using the fact that your Markov parameters are decaying. And there are many other extensions on this. And there are a few extensions we are working on, and I saw you guys are working on as well. So we got interested in doing similar things for Markov jump systems. That's something we are working on, and I saw some work from you guys as well along those directions. Okay, so I don't have that much time, but I can quickly talk about the second part as well, or we can discuss what I presented so far.
Please carry on to the stage 2. I'm sure everybody's curious to see part 2.
Okay, so this is going to be more practical, and this is motivated by learning from demonstrations. But instead of learning a cost function, I was interested in learning constraints. So Kalman's original work, it looks at the LQR problem and it thinks about learning the cost function, and most of inverse optimal control focuses on learning a cost function, and typically for an unconstrained optimization or unconstrained control problem. So why I was interested in constraints? Because although mathematically you can sort of use Lagrange multipliers or indicator functions to put your constraints into your cost function, I feel like constraints are more modular and explainable. So if you have this complex cost function that captures everything, it's a bit hard to understand. Even if you learn that cost function, you won't really understand what the person is trying to do if they are demonstrating something. Unfortunately, I forgot who said this, but it was a human-robot interaction person, and they were saying humans don't think in terms of objective functions. And if we have constraints, then we have tools from constraint control to design controllers to enforce these constraints. And from a learning perspective, one of the challenges here is that you have demonstrations that satisfy these constraints, but typically you only have positive demonstrations. So you don't want your robot to crash things and break things so that you will have negative examples. So this is, you are trying to learn something, but you only have things that from one class and you don't have things from the other class. And again, this makes the problem kind of ill-posed. Again, this is studied in different fields. We talked about inverse optimal control, but inverse reinforcement learning is also a variant of this to learn objective functions or cost functions or reward functions just by using a different system structure, MDPs in that case. There is some work in constraint learning as well. And I will also extend this from static constraints to temporal logic constraints, and there's work on learning temporal logic constraints. But the thing that we are doing here is really use demonstrator optimality as a prior. And what we observe, although we don't have any statistical analysis, what we observe is that if you have the strong prior that your demonstrations are optimal, you can learn things with much less data. So here is the problem setting. There's a demonstrator that solves a forward problem that finds this psi here is a state input trajectory that minimizes a cost function that possibly depends on some gamma that they know, but we don't know, that satisfies certain constraints. And maybe some of these constraints we know. For example, if this task is go from point A to B, we know from which point to which point they are trying to go. So this is initial and final points here. And maybe they do another demonstration for a different initial condition and a different final condition. We know these initial and final conditions. Maybe there are some shared known constraints between these different demonstrations that we will see. These could be your dynamics that determines how much you can move from one point to the other. Maybe we know the dynamics as well. But there is some unknown shared constraints between these two demonstrations that I see. So these demonstrations here are, you are telling this person to go from point A to B. Instead of going through a straight line, they are doing this weird thing because there's an unknown constraint and you are trying to figure out what that constraint is. And our problem in turn is we are given n of these demonstrations. Here I have two demonstrations. And we know maybe this known constraints. And we want to find a gamma and theta which jointly make these demonstrations locally optimal. And we possibly want to plan new trajectories that are guaranteed safe or unsafe, that are guaranteed safe by determining a subset of states that are guaranteed safe or unsafe. So what we do here is very simple. We use KKT conditions, and this is related to other optimality conditions in optimal control. It's just that since we have discrete time and finite horizon problems, it boils down to KKT. And if I write down the forward problem in this form, all the demonstrations that I see should satisfy these constraints. So it should be primal feasibility should be satisfied. I have some positive Lagrange multipliers. Complementary slackness should be satisfied and stationarity should be satisfied. And in the end, I can write down a feasibility problem where I am trying to solve for this gamma and theta and all my dual variables subject to the KKT constraints that I have. So this will give me one gamma and theta that is a feasible constraint that will make sure my demonstrations are locally optimal with respect to this constraint. But that doesn't mean that the constraints that I will find will be guaranteed safe or unsafe. To do that, what you need to do is that you need to find the intersection of these constraint sets for all feasible gamma and theta. And that boils down to a projection type operation in the feasible set of this weird optimization or feasibility problem. We also have some geometric analysis of what is optimal, what's not optimal, what is learnable, what's not learnable. And one of the key things to make this work is we are using some parametrization of the obstacles or constraints. For example, we are saying our constraints are ellipsoidal, or it's unions of ellipsoids or unions of boxes. And for these constraint parameterizations, we showed that for reasonable constraint parameterizations, this problem turns out to be a mixed integer convex problem. Of course, if you don't have any good parameterization of the constraints, the problem becomes very infeasible. So here are some examples so that I show you some robot videos. So here there is a robot arm carrying a heavy object. But there's some glassware, so it's avoiding this elliptical region. And with a few constraints, we can learn what this elliptical region is, and we can plan new trajectories with that. We also use the VR environment. For example, here you are taking a glass from underneath this bar, and you are putting it above the desk. And there are certain pose constraints on the end effector because we are carrying a liquid, so you don't want to spill it. And we can learn both the pose constraints and the location of these obstacles so that we can plan new trajectories here. And there are other examples that we have. So the other thing we were interested in is to extend this to a multi-stage version. For example, if your task is, it's not that you have a simple obstacle that you are avoiding. What if you have multiple stages of your task? For example, you want to fill in the glass, grasp the glass, and deliver it. And the challenge here is that now the problem starts having a discrete component as well. And in that case, we cannot do things with local optimality, but if you have global optimality, you can still do things in a smart way. And the trick here is that what you can do is that given some demonstration, if you know the initial and final points, or if you know some subset of the constraints, you can essentially solve for the optimal problem, optimal trajectory, by ignoring the unknown constraints. Then the thing that you know at that point, if this green trajectory is globally optimal, the red trajectory you are generating by ignoring the unknown constraints must violate the constraints. This way you can generate infinitely many negative examples. Although I told you there's no negative examples, optimality gives you the ability to generate lots of negative examples. And we are basically utilizing it to come up with a smart way of generating negative examples, and from them learning the task descriptions. And here is an example. Actually, we implemented it on a real robot. This is a VR environment where we are demonstrating a task in this VR environment. And we are assuming the demonstrator is almost optimal. And it's just taking some soup cups and Cheez-It boxes, and they are placing it in certain places. And we can learn this constraint from a few demonstrations. And here's an example of, given that constraint that you learn, you can now go and implement it in different environments. And here is an implementation on a real robot, where a robot learned that it should pick the soup box and put it into a soup can and put it into a small box and place it into this blue region. Then it's gonna go and pick the Cheez-It box. Okay, I will leave you with the robot video, and I can take questions.